Why is choosing LC values for filter design challenging? Imagine trying to tune a musical instrument where even the tiniest tweak can change the entire sound. Picking the right inductance and capacitance values for filters is just like that. It might seem straightforward, but it's actually quite tricky. The main reason is that these components control the filter's resonant frequency, which determines what signals pass through and what gets blocked. If you change the inductance or capacitance even slightly, the resonant frequency shifts. This can cause the filter to let through unwanted signals or block desired ones. Another challenge comes from real-world parts. Inductors and capacitors don't come with perfect values. They have manufacturing tolerances, often around 1 to 5%, meaning their actual values can differ from what's printed on the package. This variation can throw off your calculations and make the filter not work as expected. Sometimes, the exact values you need aren't available as standard parts. You might have to combine multiple components or choose the closest available value, which complicates the design process further. Parasitic effects also play a big role. Inductors and capacitors aren't ideal. They have small resistances, stray capacitances, and inductances that affect how they behave. When you place these components on a circuit board, the layout itself can introduce unwanted parasitic effects. These tiny influences can detune the filter or cause unexpected resonances. To minimize this, engineers need to carefully design the PCB, often making trade-offs between size, cost, and performance. Choosing the right L and C values also involves balancing different performance goals. Increasing inductance might improve the filter's ability to select certain signals, but it can also make the component larger and introduce more resistance, leading to losses. Similarly, changing capacitance affects the bandwidth and how sharply the filter cuts off signals. Engineers must weigh these trade-offs based on what the application needs most, whether it's noise reduction, signal clarity, or power efficiency. In power electronics or radio frequency circuits, the stakes are even higher. The resonant frequency must be set carefully to avoid instability in control systems. If it's too close to the system's bandwidth, it can cause phase shifts that lead to oscillations or system failure. At high frequencies, parasitic effects become more pronounced, making component selection even more complex. Large inductors or capacitors might be too bulky or costly for low-frequency applications, adding another layer of difficulty. To handle all these challenges, engineers usually start with theoretical calculations based on the desired filter specifications. Then they adjust the values considering real component tolerances, parasitics, and availability. Simulation tools help predict how the filter will behave before building it. Once built, measurements with tools like vector network analyzers help fine-tune the design. Good PCB layout practices, such as keeping traces short and using solid ground planes, also help reduce unwanted effects. So, the challenge in choosing L and C values for filters comes down to balancing theoretical ideals with real-world limitations. It's about understanding how small changes ripple through the system and making adjustments to keep everything working smoothly. That's what makes filter design both a science and an art.